Hi everyone, in this video I'm going to be talking about what is hybridization. So let's start. The first and the foremost thing before even understanding what hybridization is, that you should know it is just a theory, okay? It is not reality. Whatever we are going to study in as a part of this video is just a mathematical trick to explain bonding, and that is what hybridization is. Okay, so if someday someone asks you that, can you see hybridization happening if you have a very good quality microscope or something, just say no, because hybridization is just a mathematical trick. It does not really and actually happen. We know how we have different kind of orbitals, right? We have s orbitals, which are spherical in shape. We have p orbitals, which is dumbbell shaped, right? And it is present in three different axes, px, py and pz. We have d orbitals, which is having this kind of a double dumbbell shape, right? And we have f orbitals, which have a kind of cloudy or flowery kind of shape, which I am not very well aware of, so I won't be drawing it on the screen. My point being that we have these different kind of orbitals which we have, in which electrons can be present, okay? And we know how atomic orbitals combine to form molecular orbitals. That also we know. Clear? But the idea was that when atomic orbitals are going to combine, okay, they are not going to combine in the pure state. Like s, this is the pure s, this is the pure p, these all are pure p. Then we have pure d orbitals, okay? So these pure orbitals are not going to combine to form bonds, but before bond formation, these pure orbitals are going to undergo some kind of mixing, okay? And this mixing of orbitals is going to result into new atomic orbitals, which are called hybrid orbitals, okay? And these hybridized orbitals are going to have new set of energies and new set of properties, and these orbitals are further going to take part in bond formation, and that is what the entire idea of hybridization is, okay? Alright, so just to give it a little perspective, this is the definition of hybridization, which is mixing of atomic orbitals of equivalent energies to give rise to a set of new orbitals with new energies and properties is called hybridization. Okay, so before playing any game, the first thing what you do is you just go through the rules of the game. Similarly, before understanding the hybridization part, we'll go through the rules of hybridization, out of which the first one is combining atomic orbitals should have comparable energies, right? So this is one of the most important rules, because you cannot combine s and d together because they have huge difference in energy, okay? You can combine s orbitals and p orbitals together because they are comparable in energy, and energy is a very important factor, so which you always have to consider. So combining atomic orbitals must have equivalent or comparable energies, okay? Second rule is number of hybridizing orbitals must be equal to number of hybridized orbitals. So of course, if two orbitals are participating, we must be getting two hybridized orbitals. If three are participating, we must be getting three hybridized orbitals. And I think that's quite simple. The third one is only the atomic orbitals of the central atom having valence electrons will hybridize. Okay. So example like CH4, methane. Okay. The C is a central atom, okay, which is denoted by A, and H, the four H are side atoms. Okay. So the central atom, which is C here in this case, only that is going to undergo the process of hybridization. The atomic orbitals of only carbon are going to hybridize, and that too, the ones which are having valence electrons. Okay, we are not going to consider all the electrons, because if we keep doing that, well, the game is never going to end. Okay, so only valence electrons are going to be considered, that too only of the central atom. Alright, so no points for guessing which this orbital is. This is our very own s orbital, okay, and it has the maximum capacity of 2 electrons, right? And this is also called non-directional orbital. Why is it called non-directional orbital? Because, well, it is an s orbital and it is spherical in shape and it is not pointing towards any specific direction, right? Whereas if I talk about a p orbital is dumbbell shaped, okay, and it is present in three different axes, px, py, and pz. The maximum capacity of p orbital being 6, because every orbital is having a total capacity of 2 and it is having three different orbitals, so 6 is the total capacity here, and it is highly directional. Why is it highly directional? Because it is pointing in three different directions, in x, y, and z direction. Okay, so if I talk about the mixing of s and p orbitals, okay, so s orbital is this, and this is my p orbital, okay. So if I talk about the mixing of my x and p orbitals, the first case scenario which I can have is the mixing of one S, okay, with only one P, right? So if I mix one S and one P together, how many orbitals will I be getting? Just remember the rule. The second rule said that whatever is the number of participating orbitals, we'll be getting the exact same number of hybridized orbitals. So if we mix one S and one P, which is two orbitals together, we will be getting two hybridized orbitals. Each of them is going to be sp hybridized, okay, and we are going to be left with two unhybridized p orbitals, right? These two are unhybridized, and this is called sp hybridization, okay. So whenever we have an sp hybridization, in what cases will we have this? In the cases in which we have two bonds with central atom. So whatever the central atom, in case it is forming two bonds, okay, both these bonds are going to be sp hybridized bonds, and these angle between these two bonds is going to be 180 degrees, and the geometry is going to be linear, okay. All right. In the second case scenario, if I try to combine my 1s orbital, okay, with 2p, that is also what something I can do, right? So this is p and p. So if I try to combine 1s orbital with 2p orbitals, again in this case I will be getting three hybridized orbitals, right? All these are going to be sp2 hybridized, because as my rule says, number of combining should be equal to number of hybridized. So if three orbitals are combining, I should be getting three hybridized orbitals, right? All these three are going to be sp2 hybridized, and the last one is going to be a p orbital, which is going to be unhybridized. This is going to be the case when we have a atom or a molecule in which we have a central atom forming three bonds, right? All these three bonds are going to be sp2 hybridized, okay, and the angle should be 120 degrees, and the shape for a molecule like this is going to be trigonal planar, okay. The geometry here is trigonal planar in case of sp2 hybridization. If in the last case we can have, if I want to combine or hybridize one S and all the P's together, okay, this is my S and these are three different P's. If I decide to combine one S and all the P's together, I will be getting a hybridized orbital which will be having four hybridized orbitals. All of these will be sp3 hybridized orbitals, okay. And in this case we are going to be having a molecule which is going to be central atom, and we have four bonds. All these four bonds are going to be sp3 hybridized, and the angle is going to be 109.5 degrees, because my shape or geometry here is tetrahedral, okay. So just to give you a closure, we have sp hybridization, okay, in which we have one s and one p are mixing together, okay. The maximum capacity is going to be, of course, 4, and the structure is going to be linear, okay. In sp2 we have three bonds. The structure or the shape is going to be trigonal planar, okay. Three bonds are going to exist. And sp3, which means four bonds, so it's going to be tetrahedral. Chalo, so moving on, this is an s orbital, okay, which is spherical, so we can well call it fat, okay. This on the other hand is a p orbital, so it is long and we can kind of call it a little slim, okay. So this is a pure s orbital and this is a pure p orbital. Your hybridized orbital do not look like a pure s and pure p. In case of sp hybridization, your hybridized orbital is going to have 50% s character and 50% p character, which means it is going to be 50% fat and 50% slim. So it's kind of going to be like this. It is going to be fat and also longer and slimmer like p. In case of sp2, okay, we have 33% of s character and 66% of p character, which means our hybridized orbital is going to be somewhat longer and maybe a little less fat, okay. So it's going to be something like this. Whereas my sp3 orbital is going to have only 25% s character and 75% p character, which means boy. This is going to be very slim and trim and very less fat. Okay, so it's going to be somewhat like this. Okay, so this is what my sp hybridized orbital looks like. It's 50% s and 50% p. This is what my sp2 hybridized orbital looks like, which is having more of p character and little less of s character, whereas this is what my sp3 hybridized orbital looks like, which is having maximum p character and very little s character. Okay, so maximum s character is that of sp hybridized orbital, and minimum is of sp3 hybridized orbital. Okay, so when we talk about single, double and triple bonds, okay, we know single bonds are sigma bonds, double bonds are sigma and pi bonds, and triple bonds are sigma and 2 pi bonds, right? Sigma bonds are formed by the head-on overlap of orbitals. Okay, so we have head-on overlap of orbitals, like two s orbitals can head-on combine, which is on the internuclear axis. When they combine, that is when a sigma bond is formed. Or let's say a head-on combination of the two p orbitals, right? This is also head-on combination, or we can also say an internuclear axis, because this axis passes through the nucleus. I'll just draw it again because it's kind of messed up. So this axis, which is passing through the nucleus of the two colliding orbitals, okay, is called the internuclear axis. And when this overlapping happens head-on, which means on the internuclear axis, we have a sigma bond which is formed. When this kind of overlap happens sideways, okay, which means not on the internuclear axis, like this, sideways, then the kind of bond which we are going to get is called a pi bond, and the overlap is something like this. Okay, and because the overlap area is not that high, is not that efficient, your pi bond is weaker in comparison to that of your sigma bond. Now, as already discussed, sigma bond is formed by head-on overlap, okay, and pi bond is formed by sideways overlap. What we just discussed is the shape of the hybridized orbitals, right? How fat and how slim they are. Now, head-on overlap can be done by all the hybridized orbitals. Hybridized or even unhybridized orbitals can do it. All hybridized plus unhybridized can do head-on overlap. But when it comes to sideways overlap, hybridized orbitals cannot do that. Why? Because this is what a sideways overlap looks like. Okay, and these are your pure p orbitals, whereas a hybridized orbital looks like this, as already discussed. Okay, so because of the fat lobes which are now present in the hybridized orbitals, okay, they cannot undergo sideways overlap. Hence, pi bonds can never be formed by hybridized orbitals. Okay, so whenever we have pi bonds, for example, in C single bond C, we do not have any pi bond, right? Whereas in C double bond C, we have one pi bond. In this case, we need to leave some p orbitals which are not hybridized, so that we can combine, we can use sideways overlap there. In case of C triple bond C, again we have only one sigma bond, but the rest two are what? Are pi bonds. Again, sideways overlap or pi bonds cannot be made by hybridized orbitals, so we need to leave out extra p orbitals which are, or pure p orbitals, which are unhybridized in the unhybridized state, which will be used for sideways overlap. So in systems like this in which we have conjugation, okay, of course the single bonds are there which are made by hybridized orbitals, but we have to leave out the pure p orbitals here, okay, for all the carbon atoms, so that they can undergo sideways overlap and form the pi bonds. Let's finally talk about the hybridization of CH4 or methane molecule. Okay, so carbon here is the central atom, so we are going to be talking about hybridization of central atom, and that to the valence orbitals of central atom. Okay, so carbon is 1s2, 2s2, 2p2. So I hope you know how to write electronic configurations. Okay, the valence shell here is this much, so I will just write this is 2s2, okay, and this is 2p2. We have 2 electrons in the p. Now when hybridization is happening, the central atom is excited. Okay, so excited state looks like this. We have 2s and we have 2p, okay, and whatever pairing electron is there, that electron is going to jump to the vacant orbital, and it is going to look like this. Okay, because we need to form bonds. Okay, so we have 2s and 2p, and this is the excited state electronic configuration of the central atom. Now we are going to form sp3 hybridization here, because we have, as you see, 1 2 3 4 bonds, and all these 4 bonds are single bonds, right? So we need s and 3p to be combining to form sp3, right? So 1s and 3p are going to hybridize to form 4 sp3 hybridized orbitals, okay, each having one electron each, and these are going to finally bond with hydrogen atoms, okay, which also have one electron each, and that is going to result into your methane molecule. Okay, so methane molecule is having an sp3 hybridization, and the shape here is tetrahedron. Now let's see what happens in case of an ethene molecule. Okay, in case of an ethene molecule, we have a double bond, which means we have a pi bond. So we have 3 sigma bonds for every atom and 1 pi bond. Okay, this carbon atom is forming 3 sigma bonds, 2 with hydrogen and 1 with another carbon, okay, and 1 pi bond. Again, this carbon atom is having 3 sigma bonds and 1 pi bond. Okay, now I directly write the excited state electronic configuration of carbon, which is this 2s and 2p. Okay, this. Now I will only look at the sigma bonds for now, because I know hybridization is only going to happen for sigma bonds, because pi bonds cannot be formed by hybridized orbitals because of their fatty lobes, right? So how many sigma bonds are there? We have only 3 sigma bonds. So we need 1, 2, 3. That is why only 1s and 2p are going to hybridize together to form 3 sp2 hybridized orbitals, okay, and 1p orbital is going to be left pure or unhybridized, because this is going to be used for sideways overlap or formation of the pi bond. Okay, so every carbon atom in your ethene molecule is going to be sp2 hybridized, okay, and this is going to form with a bond with hydrogen. We have 2 hydrogens, and other last sigma bond is that of carbon, with that of carbon. Okay, so this is going to be the structure in which these are my sigma bonds, or sp3 or sp2 hybridized bonds, okay, and every carbon is going to be left with one unhybridized p orbital which has not hybridized, and that is going to be used for sideways overlap, because, well, we need to form a pi bond, right? So this is the structure of ethene molecule. The hybridization of carbon in ethene is sp2 hybridized, and only this structure, okay, this structure only is going to be considered for your hybridization part, and this is going to be having 120-degree angle, which means this is trigonal planar. Okay, so this part is trigonal planar having 120-degree angle, sp2 hybridization, and unhybridized part is this, which is left above and below for sideways overlap for formation of this pi bond. Finally, we have a molecule of ethene, okay. In case of ethene, every carbon atom is forming 2 sigma bonds and 2 pi bonds, okay. We have 2 sigma and 2 pi bonds. Only sigma bonds we'll consider for hybridization. So excited state carbon is having electronic configuration like this, okay, s, and this is 2p, and since we are only having 2 sigma bonds, we have hybridization of 1s and 1p are going to hybridize to form 2 sp hybridized orbitals, okay, with 1 electron each, and one is going to be having sigma bond with hydrogen and one is sigma bond with carbon, okay. So 1 sigma bond is with hydrogen, 1 sigma bond with carbon, that is done, and we are left with 2 unhybridized p orbitals, okay. Now these 2 unhybridized p orbitals are going to be used for formation of the pi bond which is there, because pi bond cannot be formed by hybridized orbitals. So this carbon single bond carbon with hydrogen and carbon are my sp hybridized orbitals, okay. Now on each carbon atom we have 2 p orbitals left. which are pure, which are not hybridized, right? Like this. So now these two are going to do sideways overlap to form one of the pi bonds, and these two are going to overlap, okay, which are on the other plane to form the second pi bond. So we have two pi bonds which is formed by the formation of the two p unhybridized orbitals on each carbon atom, and the rest of the sigma bonds are sp hybridized. So now I can say my ethyne molecule is sp hybridized and it is linear in geometry. Okay, so this was my ethyne molecule, and my methane, ethene, ethyne, all these are having these hybridizations. If you have any doubts in this videos, please comment that down below, and for more videos like this, keep watching.